Have you ever stopped to think about how some things in our digital lives seem totally random, like completely unpredictable?
Yeah, absolutely.
But underneath it all, they're often built on these incredibly precise, almost clockwork-like deterministic patterns. It's kind of a neat paradox, isn't it?
Really is.
Well, today we're doing a deep dive into one of those key computer science concepts, linear feedback shift registers. You'll often hear them called LFSRs.
Yep, LFSRs.
We're gonna, unpack what these surprisingly simple digital circuits actually are, how they manage to generate these complex-looking sequences, and uncover where they pop up.
And they pop up in some really surprising places, often critical ones.
Exactly. So, the idea of something looking random but being totally predictable, that's fascinating. Let's kick off our deep dive there. What exactly is a linear feedback shift register?
Okay, so at its heart, an LFSR is basically a shift register. You can think of that like a line of memory cells, maybe flip-flops, that pass bits down the line one step at a time.
Shifting bits
Yeah.
along.
Exactly.
Yeah.
But the key part is the feedback. The input bit, the one that gets fed into the start of the line, isn't random. It's a linear function of the register's previous state.
Linear function. What does that mean in practice?
Usually, it just means it's calculated using an exclusive OR, an XOR operation on some of the bits already in the register.
XOR.
Yeah.
So that's the logic gate where it's 1 if the inputs are different, 0 if they're the same?
Precisely. You take bits from specific positions, XOR them together, and that result becomes the new bit entering the register. And what's really crucial, absolutely fundamental, is the starting value. We call it the seed.
The seed.
That seed completely dictates the entire sequence of states the register will go through. 100% predictable. So even if the output sequence looks random, it's totally deterministic. No real randomness involved.
So it's that pseudo part that's key, right? Pseudo-random. It mimics randomness, but if you know the starting point, the seed.
You know every single bit that will ever come out.
Exactly. That's quite a distinction. So what's the trick then? How do they make them seem so random?
Well, what's really fascinating here is that if you choose that feedback function carefully, the positions you tap for the XOR, you can make the LFSR cycle through a huge number of states before it repeats.
A long cycle.
A very long cycle. Ideally, the maximum possible length for the size of the register. This well-chosen function usually comes from something mathematicians call a primitive polynomial. It's just a specific recipe that guarantees the longest run.
Okay, so the math ensures it looks random for a very long time.
Pretty much, yeah. And there are sort of two main flavors you see. Fibonacci LFSRs.
Fibonacci, like the sequence?
Named after it, yeah. But the structure is different. Here, you tap bits from various points, XOR them together outside the main register, and that single result gets fed back into the input. It's like a serial chain.
Okay. And the other type?
That's the Galois LFSR. In this setup, the XORing happens inside the register, kind of in parallel. As bits shift, they might get XORed with the output bit and update their own value right there.
So internal XORs, does that make a difference?
It often makes Galois LFSRs faster, especially in hardware, because the calculations can happen more concurrently rather than waiting for one feedback bit.
Right, faster is usually better. Okay, this is where it gets really interesting for me. Where do we actually bump into these things? Where does the rubber meet the road in everyday tech?
Oh, they're absolutely everywhere, often hidden in plain sight. A really common use is just straightforward pseudo-random number generation.
For simulations and things.
Exactly. Simulations, testing. The key thing here is reproducibility. Because they're deterministic, you can run a test with the same random sequence over and over. If you're debugging something, that's critical.
You need the same conditions each time.
Precisely. Or for generating certain kinds of cryptographic keys that need to be recreated predictably. Provides randomness you can control.
Okay, so controlled randomness. Makes sense. You mentioned crypto keys, so they're used in actual security.
They definitely happen, yeah. Especially in cryptography. In stream ciphers, think of things like A51, which was used in older GSM cell phone encryption, or E0 in Bluetooth.
Bluetooth uses these. Wow.
Well, yes, but here's the big but. That linearity, the very thing that makes them predictable and useful, it's also their Achilles heel in security.
How so?
Because they're linear systems. They're vulnerable to cryptanalysis. If an attacker Can observe enough of the output sequence.
They can figure out the pattern, the feedback taps, maybe even the seed.
Exactly. They can potentially predict all future outputs and sometimes even past outputs. That's obviously really bad for a cipher.
Yeah, that sounds like a major weakness. So if they're still using things like Bluetooth, how do engineers get around that vulnerability?
Good question. They don't typically use a single simple LFSR anymore for serious crypto. They use clever tricks like combining the outputs of several LFSRs in a non-linear way or making the clocking irregular. Anything to break that simple linearity and make analysis much, much harder.
Okay, so layering complexity on top.
Right. But LFSRs are also huge in digital broadcasting and communications, but for a totally different reason. Not secrecy, but signal shaping.
Signal shaping, what do you mean?
They're used for something called scrambling data or creating chipping codes. It's important to understand this isn't encryption.
Okay, not security, so what's it for?
It's for engineering reasons. Scrambling helps spread the signal's energy out over a wider frequency band. It avoids having, say, long strings of zeros or ones creating problematic spikes in the signal spectrum. It makes the signal look more like random noise.
Ah, so it helps prevent interference.
Exactly. And it's fundamental to spread spectrum techniques like CDMA used in some mobile networks where multiple users share the same frequencies. The LFSR sequences help distinguish the signals. You find this in standards like HDMI 2.0, USB 3.0, tons of Ethernet standards, Wi-Fi.
Seriously? USB and Wi-Fi.
Yep. And even satellite navigation systems like GPS and GLONASS rely on LFSR-generated sequences, those gold codes, to identify satellites and measure timing precisely.
Wow,
Yeah,
that's
wow.
way more places than I would have guessed.
Oh, and one more quick one. Circuit testing. For anyone designing chips, LFSRs are vital. They generate predictable pseudo-random test patterns to exercise circuits and find faults. And they're used in signature analysis for built-in self-test or BST.
BSD, so the chip tests itself using LFSRs?
In essence, yes.
Yeah.
They compress the output responses into a compact signature that tells you if everything worked correctly. It's really elegant.
Okay, wow. So from my phone signal to USB cables to testing the chips inside, they're kind of fundamental. What's the big picture takeaway then for us listeners?
Well, I think this raises an important point. LFSRs really embody this fascinating paradox, don't they? They're incredibly simple, elegant circuits.
Just shift registers and XOR gates.
Right, but they enable remarkably complex-looking behavior, these long pseudo-random sequences generated from purely deterministic rules. And that predictability is a double-edged sword. It's fantastic for efficiency, for testing, for certain communication needs.
With a potential weakness for security.
Exactly. It highlights that constant tension you see everywhere in computer science and engineering, the trade-off between performance, simplicity, predictability, and security.
It really makes you think, doesn't it? Maybe a final thought for everyone listening.
Yeah.
How might recognizing these systems, this sort of controlled chaos, change how you view the apparent randomness in the digital world all around you?
Yeah, it's worth considering.
How much of our daily digital experience, from that phone call connecting to data zipping across your network, is actually built on these incredibly clever, yet fundamentally predictable foundations? Something to chew on.